Hi, and welcome back to another LeetCode video. Today we're going to look at LeetCode number 94, binary tree inorder traversal. This is a super basic problem that you should be able to solve in your sleep. We're basically giving the root of a binary tree, and we should return the inorder traversal of its node values. And so what you have to know is basically what is an inorder traversal, and with that you should also know what a post-order and a pre-order traversal of a binary tree is. Those are absolute basic things. So I will explain that real quick, and then we're going to try to solve this problem. So a pre-order traversal of a tree is when you output the value of a node as soon as you encounter the node for the first time, when you traverse it basically by going into a node, then first into its left subtree, process the entire left subtree, and then into its right subtree and process the entire right subtree. So in this example, the inorder traversal would be 1, 2, 4, 5, 6, 7. Then we go all the way back up. 3, 8, 9. That's the inorder. So we returned the node value as soon as we saw the node for the first time. And when we go back up, then we are ignoring it. Now the post-order traversal works exactly the other way around. We return the value of a node as soon as we leave the node upwards. So when we process the node and all of its subtrees, that's when we emit the value of that node. So the post-order traversal would look like this. Well, we come from here to the root node. We don't emit it. We go to 2. We go to 4. There's nothing else to do. So now we go back up. So the first node we emit is 4 in our post-order traversal. Now we need to process the right subtree. 6. There's nothing to do. So we go up. So 6 is the second value that we're emitting in post-order traversal. We go to 7. Now we emit the 7. We go to 5. And now we're leaving the 5 upwards. So we're now emitting the 5. So far we have 4, 6, 7, 5. Then we go back to 2. We emit the 2. Now we are at 1, but we're not going out of the 1. We first have to process the right subtree, and we go all the way down. And when we go back up, we emit 9, 8, 3, and 1, because we try to go to the parent of 1. There isn't anything because 1 is root, but we still have to emit it. So that's the post-order traversal. The in-order traversal is when we emit a node after we process its left subtree and before we start processing its right subtree. So we would start at 1, we would go to 2, we go to 4. It has no left and right subtree. Well, it has no left subtree, so now we emit this. We try to process its right subtree. There is nothing to do. We go back up. Now we have processed the left subtree of 4, so we emit node 2. So in our in-order traversal, the nodes values that we got is now 4, then 2. Then we go back here, we go to 6. Now we have to emit 6 again. Now we emit the 5, now the 7. We go all the way back up. Now we emit the 1. And you can actually see here the order. That's the in-order. The 1, we go to the 3. We try to process the left subtree. There is nothing. Now we emit the 3. We go to 8. It has a left subtree, so we have to process it first. We output the 9. We go to 8. Now we've processed the left subtree of 8, so we emit the 8. We try to process the right subtree of 8. There is nothing to do, and we go all the way back up, and there's no parent to the root, so we're done. And it's super easy how to implement this, at least in Python, in a recursive way. And now comes the part of the code that you kind of have to know. And once you see the code, it becomes super easy to remember how to do these 3 different kinds of traversals. So the first thing that I always do is I create myself a little helper function, a def first search helper method, and it just takes a node, nothing else. And now inside that node, we basically have to call recursively our function, and we call it on the left subtree, and we also call it on the right one, just as we just did in our example. Now, if we want to have an in-order traversal, we have between calling the subtrees, we have to do something with the value of the node, right? So we have to append it to our result. And one way to do that would be, there are different patterns how you can do that, but one is to define a result outside of the helper function, result as a list. And then at the end, you could return turn result. And before you return a result, you have to call the helper function, def as helper, and we call it on the root node. And that is pretty much it, except we need to deal with the case where the root is 0, right? We could have no nodes in our tree, but we could also run into a leaf and then the left subtree and the right subtree. So this and or that would be none. So we have to have a base case. The base case is what terminates the recursion. So if we don't have a node, we're not going to do anything. But if we do have a node, we're going to continue to iterate, basically. And we now need just to add our result value, our node value to the result. And that's pretty much it. So this should already work now. And it does. There's some other nice things that you could do. For example, you could pass in a result array here and just return the result from our helper. So what we'll do here is we just return the result. So we create our list here, the one that we want to return. In the recursive call, we just pass a reference. So we're actually not copying the result list. So we're not increasing the space complexity at all. So this, let me see. Oh yeah, we need to pass it in here as well. Result. So this is just a different way of writing that code. And yeah, and it will pass as well. So yes, so what about the runtime complexity? Well, we always have to visit every node at least once. We're going to visit it twice, once on our way down and then on our way up. So, but it's still linear in the number of nodes in the tree. And with time, well, how much space are we going to need? It kind of depends on what kind of a tree we have. If all of the nodes are in one line, then the worst case is obviously O of n space, because every recursive call actually adds to the call stack. So even though we're not using an explicit data structure here to go down the tree, we are still using stack space. So that's O of h for the height of the tree in terms of stack space. But because we are basically building our result list, we end up with O of n space effectively. If we were not building up the entire result list here, we would say that we use only O of h space. So that's just something to keep to be aware of. If we don't know what the structure of the tree is, it's always going to be O of n space as well. But like a height balanced binary tree, that would have a height of logarithm of n. All right, cool. So for example, if you have a binary search tree and you're looking for a value, you know the binary search tree is balanced. If that is the case, then you would argue that you need only O of log n space, and where log n is basically then the height of that tree. Anyway, so yeah, this is super basic, and what is cool about this is now that we are emitting the value between calling the left and the right subtree, it's in order. But if we do this after processing them, we actually get a post-order traversal. So let me just demonstrate that. Of course, the test will fail, but we'll see what the post-order traversal looks like. Our example case 2. So in post-order, so this is what we're emitting. In post-order, like I said, we're emitting the value when we leave the node. So the first one is 4, 6, 7, 5, 2, 9, 8, 3, 1. So which is exactly that. So with just moving this one line, we switched from in order to post order. And if we put it in front, surprise, surprise, we actually get the pre-order traversal of the tree. So let's check that as well. So in pre-order, we should see 1, 2, 4, 5, 6, 7, 3, 8, 9, which is exactly what we see here. So yeah, so this is really handy, and you should know that, how that works, and how to implement those traversals in a recursive way.